Swayam Prabha. Digital India. Educated India.
Now, let us look at a general scenario. Let us say we have a beam which is extending. So, I am just going to cut off a small portion here and look at what forces exist within that. Okay. Since I am sectioning at these 2 points, we will have shear forces acting like this. I am just drawing the positive sense always. There is a moment acting here as shear. What is the positive sense here? It is like this, okay, and this could be x1 and this could be x2. Okay, so M at x1, V at x1, M at x2, V at x2, and there could be some load acting in between. So, let me call that as W of x per unit length. Okay. There could also be moments. For now, let us assume that we have no concentrated or distributed moments directly acting on this beam. We need to find a relationship between all these quantities that we have, M and V and W. Okay. How do we go about connecting these? We can use equations of equilibrium here in order to make a connection. Okay. Let us do that exercise a little bit more rigorously. So, I am going to take, let us say this is the reference point, there are some forces acting. Let us say I am bothered about a section at x, okay, and I would like to know how the shear force V of x and M of x is varying. Okay. Now, one way to do that is I can section a very small segment at x, let us say dx, and examine that particular small element. Okay. Let us do that exercise and see what we have. So, this is a length which is just dx in length. This is x away from one of those reference points. There will be a load acting on this, okay, with no loss of generality between this, within the small length dx, the variation can be neglected and we have W over here, W at x, okay, per unit length. Okay. This is the external force that is acting transverse in direction. Okay. Now, let us draw the bending moment. This has a negative sense like this, and therefore, we will have, this is the positive sense of shear force V at x, and bending moment will be like this, which is M at x. Since we have cut this side also, we have moment and shear force. This is M at x plus dx, because I am taking dx away from this in the positive direction, and this is shear is V at x plus dx. Alright. If V is varying from x to dx, this will show up as a different value compared to this by a small difference in the value. Okay. And if I can connect these M of x plus dx, V of x plus dx to Vx and see what we get, this may probably give a sense of the relationship between shear force and bending moment. Let us do that exercise. What all equations can we write from this? Definitely one equation that I can write is vertical equilibrium. Sigma f along y, let us say upward like this, is positive, equals 0 if it is in static equilibrium. The other is bending moment about a particular point. I can choose a center or one of the edges and draw the and find out the equilibrium of that. So, let us say m at a particular point, let us say in this particular case, shall we choose this center, m at O equals 0. We have already learned that we can take any one of those points in order to write down these moments. Let us see what we get out of these. Let us first start with sigma Fy equals 0. What all will take part in it? This shear force Vx, this shear force Vf x plus dx, and W. Okay. So, let us write one by one. This is negative in direction, so minus Vx. This is positive, so plus V of x plus dx. Okay. And there is a load over here distributed over this length, which is dx. So, W times dx is the total force and it is acting downward. So, minus W times dx, the total should be equal to 0 for static equilibrium. So, this immediately reveals, I am going to write this in a way that you already know. Is equal to W times dx. I am going to take dx down like this. Okay. Am I correct in the sign? Yes, I have taken W over to the other side. This is, remember, this is W at x. Okay. What is this? Limit. Let me just correct myself and write it as delta x here, small length. So, I am going to have delta x here, delta x here. Limit as delta x tends to 0, what is this? It is nothing but dV by dx, and that is equal to W of x. And therefore, we have a relationship. It essentially tells me that the variation of shear force along x gives me W of x, which is the load applied, transverse load applied. Okay. So, one result that we get is dV by dx equals W of x. We will get one more result from this. Let us do that separately. Okay. To be specific, I will write it as W of x. Let me denote all the forces. This is V at x, this is M at x, M at x plus dx. Notice that I am using positive sensor all of them, and this is V at x plus dx. Okay, I have represented all the forces, and this length, let me again make this as delta x so that we are clear about it. Now we seek to find the moment equilibrium at a particular point. Which point is better to choose here? We will choose one of those points. Shall we choose a point here, or a point here, or a point here? If I choose a point over here, I will not have this shear force coming into picture. If I choose a point over here, remember this particular load is equally distributed